in this lecture we are going to talk about current sensing technique in digitally controlled high power converter. This is the continuation of the previous lecture. Here we will just want to touch upon the current sensing technique, what are the non-isolated current sensing technique and isolated current sensing technique, and these are primarily used for high power converter. So, first of all, the current sensing is required for closed loop feedback control, because if you go for current mode control, then current sensing is required, and we know, and depending upon whether we want to go for peak current mode control, valley current mode control or average current mode control, then we may require different type of current sensing, whether we need to sense high side current or low side current, or we need to sense the full current. So, this all depends on the requirement of the control logic. Sometimes the control logic is decided by the available current sensing, available sense current, whether the high side current is available. So, all these things we have to decide. Then the current, in most of the cases product, they use the current sensing for protection purpose. So, that means they use high side current sensing for buck converter, if they want to protect the circuit, the peak current protection. So, that means the current sensing is that protection purpose is one, and the cycle by cycle current limit is also one, because during transient if the current overshoot is very large, then we have to limit it, because it may saturate the inductor. Then we also want to achieve fast startup, because if you go for voltage mode control based startup, then since we do not have the access, current access, or even if we have just protection current access, then in voltage mode control actually very slowly the output voltage is ramp up, or basically Vref is there is a slew rate in the Vref that is very low. As a result, the voltage will rise very slowly, but in most of the, let us say if you are talking about mobile phone and other, where we want to start the phone, that means let us say it is in the idle mode, but we want to start it up. So, for such cases the starting up of certain sector of the power management require a very fast startup, and the current mode control can help. The current sharing in multi-phase is also very much useful. We need some sort of current information for sharing the current among multiple phases. Now, if we talk about high side current sensing, this we have discussed in the previous lecture. So, we are not going to spend time on that, but this is mainly for buck converter, where we are sensing the either what is going inside the current. So, in most of the majority of the IC they use the sensing circuit inside the silicon. So, that means they can use either the current mirror, or sometimes they can use the RDS on of the MOSFET. So, there are multiple way of sensing current. The low side current sensing is easy. You can put even a small resistance at the source of the, in between the source of the low side switch and the ground, and then we can measure the current directly. But in many applications the low side current sensing, let us say in buck converter, you can implement in analog low side current sensing, you can implement valley current mode control. But in digital, even by sensing low side current, you can actually implement peak current mode control by using fully digital current mode control, where the rising slope can be emulated inside the digital controller. So, there are many possibilities exist. Now, the bidirectional current sensing. So, this is something like a full current sensing in this case. That means we are putting a shunt, that means the resistance in series with the inductor, and in that way we can sense the full current. So, this is a differential current sensor arrangement, where we are sensing the current across the resistance, and then this differential amplifier actually used to convert into differential current into a like a single ended voltage, and the voltage is equivalent voltage is getting, which is actually reflecting the sense current. Now, in the current sensing method in high power, we will use Rogowski coil, current transformer, PCB stress current sensing, Hall sensor, and then isolated current shunt measurement. So, first we will take about the Rogowski coil. In this coil, what does it do? So, the beautiful thing about this coil, that this coil, it has this one terminal here, then wrap around, then another terminal coming out. So, when a current flows through this, and it is it is kept just in wrapped around the coil, where the wire which is carrying current. whenever the current flows, and but the requirement here is that this current should be a change in current, because that means if there is a current flowing through this, then this current will cause an induced actually change in flux, because we know the Faraday's law, and this change in flux will create an induced voltage. So, as long as there is a change in flux, then only induced voltage will be developed, otherwise it cannot. So, this is mainly used for AC circuit where the current is changing, because if you take the expression of the induced voltage, it is some gain factor into dIdt, that means the rate of change of current. So, if the current is constant, then this circuit, this technique cannot be used. Now, since this technique uses the derivative of the current, so we need to do integration. That means, if we integrate this, then you will get the actual V out. If we integrate, then it will give rise to the actual current. That means, the actual current is obtained by integrating the output of the Rogowski's coil, and this overall voltage is actually analogous or the linearly proportional to the current. Now, so this Rogowski coil is a single layer coil owned on non-magnetic core, and air core output, I mean this flux, that means the air core output, and it remain linear for extremely high peak current, and this is useful for fast transient current, even the pulse current. Next, going to the current transformer. So, current transformer, again the current transformer means you have a primary side and the secondary side. So, the primary side coil actually is used, and actually if you take the primary side coil, you have to insert the wire which is carrying current through the primary side coil. That means, if you take this, you have to insert this, actually the 3 dimensional. So, this is the, let us say, current is carrying, and whenever current, so এই জায়গাটা একটুখানি ইয়ে করে দেবো তো। So, now we are talking about the current transformer, okay, CT, and you know about LEM current sensor, which uses current transformer. It has a primary and the secondary side. Typically, the turns ratio is very high, so that whatever current is going through it, that should be attenuated in the secondary side, because this current transformer should not be left open. So, there used to be one resistance here, and typically this resistance is high. So, the current should be stepped down, that means the primary to secondary current should be reduced, attenuated by this factor of the, about how the turns ratio and the current ratios are related. So, here typically in the primary side, either it can be 1 turn or the 2 turn, and this turn is made, suppose we are trying to measure current through this is a wire, let us say this is a wire, and this wire is carrying current, this is carrying current. Then what we do typically, we typically put this kind of maybe 2 winding. So, this is your primary side winding, I am talking about these 2 terminals, maybe this is connected here and this is connected, let us say here, this secondary side, or if I just reverse this diagram, this will be better. So, what I will do, I will just make on the other side, that means, so this, yeah, so this let us say this is connected here and let us say this is connected here. So, this is a primary side, instead of 1 turn it can be 2 turn, right, and then actually this so alright, but just I think this made a mistake. So, now coming to the current transformer. So, what does the current transformer do? So, let us consider a wire carrying current. So, this is an wire, this is a thick wire and it is carrying current I. Now, what we have to do, we need to put a primary coil, this is a primary. So, that means a coil, and this coil, this is a primary turn, okay. That means Then the secondary side, that means if there is a current flowing through it, then this current actually reflected in the secondary side, and then secondary side there is a diode here, and this secondary side the turns ratio is taken in such a way, if you go to LEM sensor, current transformer CT. So, this current is reduced substantially, and this current transformer of the secondary side should not be left open. So, that means we put a resistance here. So, whatever current is going the secondary side into R, that will be your V out is your IS into R. So, this R is typically 1 kilo ohm or maybe hundreds of ohm, and you need to accordingly decide. So, this IS and IP, that will be related by this turns ratio, and then you will get the actual. So, this current which is going through it, and this is converted into the secondary side. Now, in this current transformer, we need to put a diode. Why do we put a diode? Because when the current, because if you go to the transformer is required, if you disconnect this path, suppose if the current is negative, then what will happen? If the current goes negative, for positive current this is fine, negative current this flux has to be reset, that is why the diode is there. Okay. Once more. So, this is a current transformer. In the current transformer, one of the example is the LEM current sensor, which is current transformer. So, the primary side coil, actually whatever current is passing through, that actually goes to the secondary side coil, and the secondary side there is a diode. And now, how does it work? That means it is by means of a current transformer principle, and the step down ratio is quite small, the current, so that the secondary side is current is low, and secondary side should not be left open. So, you need to put a resistance. So, the secondary current into resistance will give you the equivalent analogous current which is flowing in the primary side. Okay, and this is a turns ratio. So, V out equal to IP NP by NS, where IP is the primary side current and NP is the primary side winding turns ratio and the secondary side turns ratio. So, in the current transformer, the secondary side actually so it should have a low output impedance, and it gives you an isolation between the power circuit and the control circuit, and the power loss can be reduced in this case. The transformer should have a very low power loss, and this kind of sensor also gives you high signal to noise ratio. And the requirement of the current transformer should have a very high magnetizing inductance, so that the current magnetizing current should be very low, and the saturation flux should be high, so that it can swing to large extent. The coil loss should be reduced, and also size and the cost should be reduced, and then if you take a toroidal kind of shape, then you can also minimize the leakage inductance. Now, if you are going for PCB trace current sensing, typically what we do through a PCB trace current, so it generates a magnetic field, the PCB trace, because whenever the current flowing through the trace, any current flowing through a trace, it will create a magnetic field. The magnetic field detected by a sensor. So, you will place a sensor here, and then the high current measurement and the non-contacting current sensing, this technique, because you are not physically cutting the path, you are just putting on top of the current path, that means, and then, but this sensor actually you have to be non-invasive sensor, that means you are not breaking the loop, you are just touching on the path where the current is flowing through. The Hall sensor is another kind of very important sensor, where what is the Hall sensor principle? So, Hall sensor works in the principle that it has its own voltage. Actually, this is a sensor, Hall sensor, and if you keep this sensor close to the magnetic field, because if the current is flowing through this path, and then it will create a magnetic field, and this magnetic field will actually influence the voltage produced across this sensor. This voltage produced across this sensor will be influenced by the magnetic field. That means, if the magnetic field changes, the voltage will changes, and that will capture the current flowing through this conductor. So, that means the DC current sensing with electrical isolation, there is no physical connection, and the voltage produced across the current wire carrying conductor under influence of the magnetic field. So, that will be the voltage, and this voltage of the Hall sensor is nothing but is a constant I into B, where I is the current flowing through this and B is the magnetic flux density. So, the advantage of Hall sensor can be small size, low cost, linear response to the magnetic field, DC current sensing with an inherent isolation capacity. Disadvantage, it has a low sensitivity and range of linearity is limited. Another current sensor is the isolated current shunt measurement, where if you are sensing by means of a shunt current, that means the current is this flowing through the shunt, and we also need an isolation, then we can use an isolation amplifier, and this amplifier output is in the differential form, and then we have to take the we may have to use another stage of differential to single ended conversion. So, by that way you will get the voltage corresponding to the current flowing through that high current path. So, typically AMC 1200 is one of the example of the isolation amplifier. It has high input impedance, low current drawn, and then high voltage isolation capability. So, in summary, we have discussed various current sensing technique, we have discussed non-isolated current sensing technique, and we have also discussed some isolated current sensing technique. So, with this actually we will go into more of the hardware implementation, and we will present what current sensing we have used in our PCB for this teaching kit and which will be used in this particular lecture. That is it for today. Thank you very much.